Okay, let's talk about symmetric group Sn. So Sn means the group of permutations of 1, 2, 3, 4 up to n. It's a group of order n factorial. Here are the first three. S1 is just the trivial permutation, so it is the trivial group. S2 is a group of order 2. So it has the trivial permutation that takes 1 to 1, 2 to 2, the identity element, and the permutation that takes 1 to 2, 2 to 1. You write it like this. Okay. And then S3 has 6 things. So here is, for example, a typical thing of S3. What sort of creature is F? F is really a map from 1, 2, 3 to 1, 2, 3, not just any map. It has to be a 1 to 1 onto map. Onto what is called a bijection or an invertible map. Here's the most naive picture of F. 1, 2, 3, 1, 2, 3. What does F do? Takes 1, 2, 2. I'm talking about this F. 2 to 3, 3 to 1. Rather than writing f of 1 equals 2, f of 2 equals 3, f of 3 equals 1, rather than writing all that, we just write this, which is more convenient. And similarly for the other ones. And we know how to multiply two such permutations. You just apply them back to back. Like if you call this f, and then call this g, let's multiply them, f, g. When you multiply them, you have to apply them to 1, 2, 3 and see what you get. So fg of 1 is f of g of 1. What is g of 1? Is 3. G of 1 is 3. And then what is f of 3? It's 1. Because fg of 1 is 1. So fg starts like 1 goes to 1. Now you track 2 and 3. Fg of 2 is f of g of 2. G of 2 is 1. So that's f of 1, 2 again. So 2 goes to 2, and then 3 has to go to 3. So this is really the identity. So f times g is identity. You can check g times f is also identity. So this g is the inverse of this f. That's how multiplication works. Here are two elements of S6, something bigger. When I multiply them, beta alpha, you have to remember I'm applying alpha first and then I'm applying beta. Look here. When I'm doing fg, I'm taking 1 and then applying g first and then applying f, right? When you applied g, you got 3, and then you applied f, you got 1. So you write it beta alpha, but it's really first apply alpha, then apply beta. Please remember that. So let's do this. Let's just do it quickly now. Getting better, I hope. So 1 goes to 4 when you apply alpha, and then 4 goes to 2 when you apply beta. So 1 goes to 2. So 2 goes to 1, 1 goes to 3, so 2 goes to 3. 3 goes to 2, and then 2 goes to 5, so it goes to 5. 4 goes to 6, 6 goes to 4, so 4 stays at 4. 5 goes to 3, 3 goes to 1, so 5 goes to 1. Then 6 has to go to 6, 6 goes to 5, 5 goes to 6, yes. One way to visualize such a permutation, sigma, is to think of 1, 2, 3, 4, 5, 6 in a box and think of sigma as moving them around. And sigma moves them around like this. It takes 1 to 2, 2 to 3. So this is a picture of sigma, let's say. 3 to 5, and 5 back to 1. And then it fixes 4, it fixes 6. Right. So it turns out that writing all this is still redundant. Actually, you could just express it by writing 1 goes to 2, goes to 3, goes to 5, goes to, and when it goes back to 1, I'm just going to close the parenthesis. Now what you have found, this sort of a permutation, it's called a 4 cycle. A 4 cycle. And what you have written here is called the cycle notation for this thing. So maybe I'll call this a 2-column, 2-row notation. And this is a more abbreviated notation. There's some confusion whether you want to call this thing. If I just write like this, it's not clear if I'm talking about the element in S5 or in S6 or maybe in S20. But of course, they sit in each other in this way. And it will be clear from the context which one we mean. Otherwise, you could just take the smallest one. So we have a notion of a cycle and cycle notation. The general definition is written out in the notes. A k cycle is going to be a permutation which moves k elements out of 1, 2, 3, 4, n in this cyclical manner and fixes everything else. So the other things don't move. All right. This alpha happens to be a cycle too. Let's check. Let's start with 1 and track. 1 goes to 4, 4 goes to 6, 6 goes to 5. Please keep looking. 6 goes to 5, and then 5 goes to 3, and then 3 goes to 2, and then 2 goes back to 1. So I close the parenthesis. So this is a 6 cycle. Okay. All right, so we have cycles, but not every permutation is a cycle, of course. If you take this beta, you can see that it's not a cycle. But it's composed of certain cycles, you see. Let's see what beta does if I do it like this. 1 goes to 3, 3 goes back to 1. Okay. And then there is 2, which I haven't figured out yet. So 2 goes to 5. So this is a picture of beta. 5, and then 5 goes to 6. And then 6 goes to 4. And then 4 goes back to 2. So it's not a cycle, but it's really composed out of 2 cycles. In fact, if you call these cycles beta 1 and beta 2, what I mean is beta 1 is the permutation that just switches 1 and 3 and fixes the other 4. So when I don't put a row, I mean I'm fixing them. And if beta 2 is the permutation that fixes 1 and 3 and moves 2, 5, 6, 4 in the cyclical manner. So beta 1 in cycle notation will be 1, 3. And beta 2 in cycle notation will be 2, 5, 6, 4. Then you note that your beta is really beta 1 times beta 2 or beta 2 times beta 1. In fact, these two commute. First applying this permutation and then that one is same as first applying beta 2 and then applying beta 1, because whatever beta 1 moves, beta 2 does not touch. And whatever beta 2 moves, beta 1 does not touch. So if you do it in either order, the order doesn't matter. And beta is actually a product of these permutations. The permutation which in cycle notation is written as 1, 3, and then the permutation that in cycle notation is written as 2, 5, 6, 4. So that's how you get cycle notation for a general permutation. And if you just analyze what you have described, this procedure can be easily turned into an algorithm, and looking at this algorithm you get a proof of this following theorem, that every sigma in Sn is a product of disjoint cycles. Disjoint as in the things that this one moves and the things that this one moves have nothing in common. The numbers that appear here and the numbers that appear here have nothing in common. And further, disjoint cycles commute. So like beta 1, beta 2 is same as beta 2, beta 1. So the order really doesn't matter. There are various things the cycle notation is good for. It's definitely shorter, but it's also, using it, you can compute various things. So let's actually write down cycle notation for this mu. This is an element in S9, something bigger. So this will explain the procedure even better, I think. What I do is I start from the smallest number and track what happens if you repeatedly apply this element mu. So 1, when you apply mu, goes to 1, when you apply mu, goes to 5, when you apply mu, goes to 2, when you apply mu, goes to 8, and then when you apply mu, goes back to 1. Okay, so I came back to 1 and I got the cycle 1, 5, 2, 8. So these, I know what happens when I apply mu 2. So what's the first number that I haven't worked out yet? 3. So we start there now, just goes to 3. Then I go to the next thing that I haven't figured out yet, 4. Goes to 7, 7 goes to 9, 9 goes back to 4. And then the only thing that is left is 6, goes to 6. This is called a cycle representation of mu, and I'll say a definition: cycle type of this mu is going to be 4, 3, 1, 1. So what I've written down is the lengths of the cycles. The cycle type it's a rather interesting invariant of a permutation, and it plays a role, we'll see. And when you write it as in the cycle form, usually you just omit the single length 1 cycles, the things that don't move. So you just write 1, 5, 2, 8, 4, 7, 9. You omit the 3 and the 6. You can figure out that whatever doesn't show up is being fixed. So here's, for example, one thing the cycle notation is good for. This is a reasonably easy exercise. Show that if sigma in Sn has cycle type n1, n2, n3, etc., nk, and usually we write them in decreasing order, then the order of this guy is the least common multiple of these numbers. And this is easy to understand. If you look at this example, for example, mu, what does it do? It moves 1, 5, 2, 8 in a cyclical manner, and moves 4, 7, 9 in a cyclical manner. Fix the other two guys. Fixes 6 and 9. 3 and 6, I'm sorry. So if you do it after 4 times, if you apply mu 4 times, these guys will come back to themselves. So these come back to themselves after every 4 times. These come back to themselves after every 3 times. You want to know how many times I have to apply mu so that everything comes back to itself. That would be the order. And that number is certainly the LCM of 4 and 3. So this mu, for example, has order 12, etc. Another thing that cycle notation tells us is how to calculate conjugates of elements. Maybe we'll take that up next time, and then we can find nice set of generators for the permutation group.